All right, so you may have noticed that I drew my carbohydrates a little bit weird. These are what's known as Fischer projections. Let's talk about Fischer projections and the stereochemistry in them. So one thing that we have to realize with biochemistry is that the shape / stereochemistry is very important. The change of the shape or the stereochemistry of a molecule, and it can behave completely different. So let's go ahead and take a look at this. Draw this compound right over here. And this one is our glyceraldehyde. And it's our most simple carbohydrate. It's a triose because it has 3 carbons. It's also, we can see the stereochemistry is R, right? So let's go ahead and just confirm that. Our highest priority group is going to be this alcohol. The second highest priority group is going to be this aldehyde. Third will be this carbon attached to the OH. And then fourth will be the hydrogen. So use your right hand rule or whatever you like to identify stereochemistry and confirm that is indeed R. It's also known as plus glyceraldehyde. And that has to do with the way that it rotates light, which is related to the R configuration. And then finally, it can also be called D glyceraldehyde. And so D is basically just another way of saying R. Don't worry about why. It just stands for D is dextrorotatory. Can't say that word. Dextrorotatory. Right, the positive is the way that it rotates light. Cool. All right, so let's try to change this from our kind of normal way that we draw our tetrahedral carbons to our Fischer projection. So the first thing that we're going to do is basically just make it kind of look more like 90-degree angles. So we're going to have the central carbon, which is this carbon right here. And then coming out of it is an aldehyde. So we'll label that as CHO. And then we're going to make that a dash as those going into the back of the board. And then take this kind of methanol group, right? Put that in the back of the board as well. And then we're going to make the OH and the H as wedges. Don't worry about this too much. You won't be asked to convert from one structure to the other. And then basically what we do is we get rid of the wedges and the dashes, and then that's our Fischer projection. So up here we have our aldehyde. Down here we have the carbon attached to the alcohol. Here just the alcohol, and then here's the hydrogen. So over here and over here there are implied wedges. And then over here and over here, there are implied dashes. And then this is what's known as a Fischer projection. It's just another way to draw these sugars. And as we go through this section on biochemistry, and if you go further into biochemistry, you'll notice that biochemists have their own sort of notation, which often differs from what we learned in terms of organic chemistry. So let's take a look at D-glucose. Right, and then go ahead. I want you to pause the video, identify all of the stereo centers, and then identify whether there are or S. All right, so hopefully you've done that. You'll identify this stereo center as R, this one down here as S, R again, and then R again. There's different tricks to do this quickly, or you can just use the right-hand rule. What you'll notice is that if the OH is on the right side, it gets R. If the OH is on the left side, it gets S. But anyways, there's the Fischer projection. Here's how we kind of conventionally draw it in our kind of organic chemistry courses. Right, so there's D-glucose drawn as well, right? And then I'll just label all these carbons. That way you can orient yourself to them.